a lot of people aren't here in the live session, we can still have them people can still watch the recordings, I suppose. So we don't want to be too late. Okay, so welcome back, everybody. Um, Last time we left off, we just defined smooth manifolds. So today we're going to start with a brief recap of what we did last time, although I want to try to make sure that doesn't take too long. And then we're going to define two important spaces on our smooth manifolds that are only definable once we have this smooth structure. And those are called the tangent and cotangent spaces. Okay, so first the recap. So we have we start with just say we start logic because we really didn't send it that so spaces that don't have any smooth structure that with more said that the space needs to be Hausdorff. Secondly, we said that the space needs to be second countable, which means that its basis needs to be countable. Uh, and thirdly, and this is kind of the most important point, it needs to be locally Euclidean. Once we add these three properties, we get something called a topological manifold. A topological manifold is still that kind of stretchy space, but we've discluded a lot of uh, spaces where some odd behavior happens that will prevent us from doing sensible geometry. So um, once we have this topological manifold, we then started to try to do calculus on this. So um, let me just say calculus. In order to do that, we started defining coordinates. Coordinates. We defined charts. Well, I say coordinates. I mean, like charts are coordinates. So um, are how we define coordinates. So I'll just say charts. We define chart transition maps. And we define something called CR compatibility. And with all three of these, we were able to lead to something called a CR atlas, which then led to something called a very specific type of CR atlas is a CR differentiable structure. And adding this structure, this is that structure that we wanted to add to do calculus. So adding this structure gave us finally a CR differentiable manifold. It's a manifold on which we have some sensible notion of coordinates all over the manifold. And when we move from one part of the manifold to another part of the manifold, we don't lose the CR differentiability of any function that's defined on that part of the manifold. So the calculus across the manifold is consistent. So that's basically what we did so far. And if we quote unquote, if we set R to infinity, we get a smooth manifold, and that's where we ended off last time. So that means that infinitely differentiable functions on some chart will be infinitely differentiable no matter where you and that consistency will be there. So we have smooth manifolds. So smooth manifolds have these two interesting, well, they might have more spaces. We're not concerned with that right now, but primarily they have these two interesting uh, spaces that can be defined on them, which are called the tangent space and the cotangent space. And the fact that their names are similar or have this pattern is not a coincidence. They are very closely linked to each other, and we'll see how they're linked to each other as well. Okay, so that is a recap. Um, before we get on to the main part, does anyone have any questions about what we did last time? I don't have the chat open. I'm just gonna open the chat real quick. Why do I see thunder flashes? Oh, yes. There's a lot of traffic outside, and it sounds like thunder flashes, I suppose. Uh, I don't know. I live in a suburb, but somehow it gets blocked every evening. On the screen, oh, is the recording glitching out on your end as well? Okay. Oh, I was worried about that actually. We will fix that next time, hopefully. Okay. So let's go to the next page and let's start on defining tangent spaces. So tangent spaces. So what is a tangent space? So first of all, let's kind of try to understand the idea of where tangent spaces are coming from or where we're getting the idea of tangent spaces. So, regular calculus, we have a function. Let's say this is t. Then if we have this curve, we might say that this axis is telling us f of t, or let's say for purposes later, we'll call this gamma of t. And so this is a curve in R2. And let's say we choose a point on this curve. Let's call that point t prime. Then we might draw a vector that points in the direction of that is right along this curve, touching it at only one point. And you can prove that there is only one such there's one line on which um, these can exist that touches the curve at only one point. Any other line will intersect that curve at 2 points. So this is what we call a tangent vector. And so what we really want to do is we want to promote this tangent vector to a general manifold. And so in this situation, the tangent vector is, the manifold is the analog for this. So this curve is what we're going to generalize to be the manifold. In fact, this curve is a manifold, and so you can think about it the other way around, that whatever definition for a tangent vector that we'll come up with will have to boil down to this tangent vector when we have the curve be the manifold, this kind of curve be the manifold. But Yeah, the idea is that okay, so how do we capture this idea of like what does it mean for this vector to be tangent? Well, can we do it without taking reference to the fact that this is 2D space? Because actually this curve is one dimensional, right? It only has one input parameter, which is t. So could we do this in a way that only takes reference to the input parameter? What this is called an intrinsic definition. So how could we intrinsically define this? And without reference to the ambient space that we are working in, we've embedded this blue line in this 2D grid, right? We want to not make reference to that 2D grid. So what we could do is we could have this point on uh, here on this on the curve, and we could think about how does it move along this curve, and if we track the change of this point on the curve, then we can uh, find out its instantaneous velocity. And its instantaneous velocity, according to calculus, will give us an arrow that is tangent to that curve. I'm not getting into all of this in detail because this is stuff that is like you go into detail in multivariable calculus and such things. So we're going to focus on the manifold version of it. I'm just making reference to what you've learned about already. So first of all, we need a way to have this parameter t that as we move along the curve, we can use t to move along the curve. So that's something called. So what we want is something called a parameterized curve. And this diagram, to an extent, gives away how we're going to do that. We have this real line, which is the x-axis, quote unquote, the t-axis, um, uh, and this is a copy of R. You could think of it, and this is a copy of R. And so what we're doing is we're saying that let's map this parameter t, which is comes from this copy of R, up to R2. So so in that case, the manifold would be two-dimensional. So you could think of this curve as tracing some path through 2D space. So, but what if that space is more general? Then what do we do? So the idea is that let's say we have this map gamma p, which we take on the real line. It takes inputs from the real line and it gives you as an output points on the manifold. So what that looks like is we have this manifold. I'm just going to draw a part of the manifold. And we have this point on it, P. And we have a curve where P is a point on that curve. So we could think of this curve as a piece of thread. If we think of it as a piece of thread, let's straighten that piece of thread out. And that's our copy of R. But in general, we want this, we only need, in order to define something like a velocity vector, we don't need the curve to go off into infinity on both directions. So just to make it more general and more applicable to more situations, we're just going to say that it's local to this. Let's say that this is a U, UP, which is a subset of M. This is an open set. And we need it only to be defined on this open set. So we say, let it be centered on 0 and go from minus delta to plus delta. So one thing I want to be careful about here is that this is not the only way you can parameterize a curve. This is a very specific way to parameterize a curve. We're going to call this a parameterized curve that is centered at P. But for our purposes, it's just a tool that will be enough to define a velocity vector. So we can show these endpoints on the manifold, and those are going to be over there. So we forget about the rest of R, and we just focus on this subset. So we restrict R to be this open set on uh, on R. And we know that this is an open set because we're using the standard topology on R. Okay. So and one condition, which the reason why I called it gamma p, and the reason why it's called centered at p, is that gamma p of 0, the point at the center of the curve, should map to the point p. In fact, let's color code that. Yeah. So this point here maps to this point here. So again, we can think of the point as tracking along this curve, and when we take the derivative of that point, we should be able to get an arrow that is tangent to that point at the curve. That's what we're looking for here. So in order to do that, we need to define what a velocity vector at a point, let's call it p prime, what that means. P prime at p prime on M. So this is something we don't know what it means. You might look at this and say, okay, well, we know what a velocity vector is. Yes, we do. Again, we do know what a velocity vector is on Rn. And we're trying to lift that onto our manifold. We don't know what a velocity vector means on our manifold yet. So that's what we're going to try to define here. So let's start with our curve, gamma p of t. And all we require is that p prime is some element of up. It's inside our the local chart that we are working in. But remember that gamma p returns points on the manifold. So in order to work with that, what we established last time is that we have to coordinatize everything. So how do we coordinatize everything? Well, we use a chart. So this is our chart. It's the homeomorphism that's associated with the open set UP, and we're guaranteed to have that homeomorphism because we're working on a manifold, and we know that on a manifold, any open set, which we're assuming all open sets are in the topology, so any open set has a homeomorphism to a subset of Rn. So this is well defined, and it takes on one hand elements in R, and well, generically elements in R, but really elements between minus delta and plus delta. And it gives us, this is a little bit awkward. I mean, the way we write functions is the other way around. So this is the input, this is the output. So the output is in Rn, where n is the dimension of the manifold. But if we have an output in Rn, we know how to take the derivative of it, right? So, well, sorry, its input is in R, so it's actually a single variable function. And so if it's a single variable function, we don't even need to use multivariable calculus. We can just take the single variable derivative that we all know about. And in order to take its derivative at a certain point, its value at a certain point, we just say that, okay, we'll take t is equal to t prime, where phi up of t prime is equal to p prime. So what we're basically saying is that let me use a different color to make it stand out. Okay, so let's say that t prime is some other point, and that maps to a point here, p prime, using our chart. Or let's put the arrow this way, because then that's phi u of p, or phi u of p. Oh, right. This would have to be the other way around. This takes points on the manifold and it gives us points on in the real space. So, oh, sorry. No. That's not it. Gamma p of p prime is equal to t prime. Yes, that's right. Okay. So, from here, we just define that this is what it means for gamma p to have a derivative. So this is gamma p prime of t prime. Or you could call that d gamma p dt. But you have to be careful here because um, this ddt is not the same ddt as this one. This is the one that we know and love, and this is a new one that we've defined because it does, and we've called it the same thing because it does the same thing on our manifold. But this is defined on M, and this is defined on Rn in general. Or in this case, it would be R1, not to confuse people. In this case, it would be R1. So, but this allows us finally to define a velocity vector. But before we do that, there's one kind of caveat, one sticking point, which is that let's say I draw an open set on our manifold with P on it. Let's take this like aerial view of that part of the manifold that we had drawn before. And so what if there are two curves, right? Maybe there's a curve that looks like this, and there's a curve that looks like this. Well, in that case, their velocity vector would be the same. It would point in this direction. Let's just assume that the parameter is moving at the same rate along these curves such that the magnitude is also the same. But you could see how there could be two curves where the velocity is the same. So we have to make sure that we have a unique value for the velocity. So what we say is that Vp, that's our velocity vector, is defined to be d gamma p dt, where this is this one. Sorry, is this one at t equals 0, because now we're talking about only the point P. For a parameterized curve centered at P, we're focusing on the velocity vectors at P. That's the reason why we made that distinction in the first place. We defined the velocity vector at any point on the curve, but we're specifically focusing on the one at P. As long as gamma P is an element of the equivalence class gamma P. Now, what is this equivalence class? Well, we're about to define it. So this equivalence class is defined where two curves are equivalent if well, this whole thing, if d dt of phi u p after gamma p of t at t equals 0 is equal to d dt of, I won't have enough space here, so let me move that a little bit, of phi u p after, let's say the other curve is lambda p, then lambda p at t equals 0. If these two are equal, then we say that they're equivalent. What does that mean? That means that if their velocity at that point is the same, that's what we're trying to specify here. Oh, there's a question. One second, I'll come to the question. So what we're trying to signify here is what we mean when we say we want their velocity to be the same. We want to put them in this equivalence class only if their velocities are the same. What do we mean rigorously when we say that? We mean this expression here. So gamma p of t and lambda p of t have the same velocity if this is true. So we get a unique velocity vector for each of these equivalence classes. So you can think before we had more curves and we put those curves in a set of bins based on the fact that they had the same velocity according to this criteria of having the same velocity. Okay, so let me come to this question. Does not gamma p prime give back an element in the manifold? I was thinking we get t prime after we compose phi u and gamma p and acted on p prime. Let me see if I can translate what you're saying here. Um, we get t prime after we compose phi u and gamma p. Well, okay, let me spell out the types of these to make it simpler. So gamma p takes us from R, a subset of R, but R, to M. And phi u p takes us from M to Rn. So the composition of these is a map that goes straight from R to Rn. I hope that answers your question. Yeah, this isn't, I didn't know if I should take some time to explain this idea because to some people it's completely foreign and to some people it's almost so trivial as to not be mentioned. But this idea of function composition and making sure that an object is the right type to be put into a function, I think is something that helped me keep a lot of differential geometry straight. Um, so yes, if you want to do this operation here, you have to make sure that this space and this space are the same. And then you get a function that goes from the first space to the last space. Okay, hope that helps out. I'm going to erase that. Right, so let's continue. So that is a velocity, and we are at the home stretch here. So for tangent spaces, that is. So a tangent space, very simply, is just a set of all unique velocity vectors at P. Unique velocity vectors at P on M. And we call this space T, T for tangent, P for the point at which we want to attach the tangent space, and M, well, some people will have the M in a bracket and some people won't. It doesn't really matter, but this is it. TPM, that's what we call it. That's how you pronounce it. That is the tangent space at P on M. And you can kind of think of it again with two-dimensional surfaces. You can think of it as this is P, and there's actually a very important point to make here. It's attached to this point on P, and you can see here the analogy between this and what we had with the curve here, where this plane. Let me see if I can draw it with the same colors to make it make sense more. So this would be the plane, and so it might be produced from a curve that's along the manifold gamma p. But I mean, you have to think of this as there being all of the curves, any curve that goes through P. Let's say this is lambda P. This will also have an element in there. So this will have a velocity vector in this. Let's say that's W P, and this blue curve will have a velocity vector that might be VP. And so the set of all velocity vectors will form this space TPM. Now, the claim is that TPM is a vector space. I know it's very shocking. We called them tangent vectors and now it's a vector space. TPM is a vector space. We're not going to prove this because it's very tedious to prove it, but we're going to look at some of the evidence that it's a vector space, and I hope I can convince you. So we need a notion of addition. So I'm going to go over this really quickly. We add the velocity vectors, right? We add the d gamma p dt's, and we use the addition that's defined on the derivatives in order to define addition. We can define scalar multiplication very similarly. We multiply c times d gamma p dt. Yeah, so like d lambda p dt, t equal Remember the t equals 0 here. It's very important because they have to be all at the same point. If we have two different points, they're two different tangent spaces. So like if were at point Q, then we would have TQ of M, which is a different space from TP of M. Okay, so we have a zero vector. The zero vector is it corresponds to the curve where we gamma p of t is equal to p, right? So we stay on p the entire time. So if the point of that we're scrubbing across this line never moves, then its velocity is 0. Right, so that's our zero vector. And we have inverses. Um, inverses where if you go yeah, gamma p of minus t would just give you the or sorry, gamma p of delta minus t, something like that. Well, basically we're going backwards. We're going, instead of going from minus delta to delta, if we go from delta to minus delta, we get the opposite velocity vector at p. So we have all of the inverses. So for all gamma p, there exists some minus gamma p. So TPM is a vector space. Okay, so that's it for TPM. And now we're going to define its cousin, cotangent space. And that will be the last point for our lecture today. Cotangent space. Oh, right. Before we talk about cotangent spaces, I forgot to mention something. I'm going to go over this very, very quickly. There's a much bigger description of how to do this in the notes, but I think that it's pretty self-explanatory. Or the details that you'd like to read are better read, and I think it's better if I just go over what the intuition behind this is. So we defined VP to be the derivative, right? So it's some d gamma p of t dt, but we can decompose that using chain rule, right? Using our understanding of chain rule. So this turns into partial gamma I. So gamma I is the ith coordinate of gamma. So you could think of that as gamma I of p is equal to ui after gamma p of t. Did I get that right? Yeah. So we can use chain rule. So if we use chain rule, then what do we get? P element of m d gamma I t dt at t equals 0. So then, yeah. So this has the structure that if we were to say that, well, VP is a vector, so we should be able to decompose it into a component, VIP, into a basis vector, EI. And so then this is our basis vector. They come in the opposite directions. I didn't really want to put this on the other side because there is kind of like an order to these things, but since they're operators, but this is the basis vector and this is the coefficient, which that makes sense. The coefficient of the velocity vector is the velocity in that direction, right? This is the part of the function that's moving in that coordinate. So this is the velocity in that direction, and this is called the coordinate vector basis. And a very important thing about vector spaces that I will repeat here because it's very important is that EI is not always this partial derivative. This partial derivative is the coordinate basis. It's the basis where you take all of the basis vectors to be along the coordinate, along one unit of the coordinate. Of course, EI could be a more complicated basis, right? Like we've all seen that bases can look something like this as well. where one of the basis vectors is like that, one of the basis vectors is like that. So this is a basis vector. So let's say that's E1. That's a coordinate basis maybe, or maybe it's even longer than a coordinate basis, right? Maybe the coordinates are over here, and this is E2. And this one definitely is not along the coordinates. So E1 and like EI do not have to be these partial derivatives, but they will be linear combination because this will form a basis. Um, this set, uh, partial partial gamma I at P, uh, where I is equal to 1 to n. With this will form a basis. This is the coordinate basis. So obviously, these only have to be linearly independent, and these are also linearly independent. So we can express one set in terms of the other set. Yeah, but in general, keep in mind this is uh, not tied to a specific coordinate system. Um, uh, it only gains a specific meaning once you attach the coordinate system, but it's not like it can mean various different basis vectors. In fact, there's a subtlety with the indices, and I'll get into it if anyone is interested after the lecture is over. Okay, so that's fine. So let's start with cotangent spaces. So the easiest way to define cotangent spaces is to start with tangent spaces and define an operator called the directional derivative, and link that to the cotangent space. And this is where you can see where the tangent space and the cotangent space are very heavily linked together. Whether you use coordinates to do that or you just use this map the directional derivative, they do have these special relationships with each other. So what is the directional derivative? Well, if we the directional derivative is a map dvp that takes you from a space called C infinity M to R. So C infinity M might be somewhat self-explanatory, but just in case, C infinity, we were calling C infinity functions that are smooth. So C infinity on M is functions that are smooth on the manifold. This space wouldn't even make any sense until we defined all of the things that we did last time so that we had smooth functions on the manifold. But it takes a smooth function on the manifold and it outputs a real number. Okay, so how does it output a real number? Well, we take a function on C infinity M, uh, and or from C infinity M, and we decompose it like this, where this set xi, oh, I call this M, but it should be N. Uh, this is a coordinate basis. Right. Um, and then you could translate this to any other basis given the rules of vector spaces. So this is the directional derivative. It has the same properties as if you've come across the directional derivative before, then this is exactly the same thing. It takes a vector and tells you the rate of change of the function on the manifold. Let me visualize this. Um, let's say we have this function that is like varying on top of the manifold. So you can think of it like this curvy space that's on top of the manifold, with the value of the function being the height above the manifold. And we have this specific point P on the manifold. If we trace that up to the point on the function, then it will tell you, let's say that's the direction uh, of VP on the manifold. We translate that up, and it will tell you how much the function is changing in that direction. But it will multiply that change by the magnitude of the vector. So if you want just the change in the function by itself, then you need a unit vector in front. And if you think about, okay, well, what if I took a vector, the basis vector in the x direction, the basis vector in the y direction, and dot, 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 all the basis vectors up to the n direction, you actually get the gradient. The gradient of the function is the sum of the directional derivatives along all of the velocity vectors. Or sorry, along all of the coordinate basis vectors. So we're going to use this to define what a cotangent vector is. A cotangent vector, sorry, did I skip a little bit? Yeah, I just skipped a little bit. So one thing we're going to need before that is figuring out what the differential of a map is. So let's say you take an element from C infinity P of M. Now this might be self-explanatory at this point. Take C infinity M and take, okay, well, it's not completely self-explanatory. You need a local neighborhood, UP, around P. And if we restrict the functions in C infinity M to that local neighborhood around P, then we get the space C infinity PM. These are called, for some reason, I think this is part of that wheat analogy that they keep using in mathematics. This is called the germ of a function on the manifold. So if the wheat analogy makes sense to you, maybe that helps. But the differential, let's say f is an element of here. So then dfp is a map that goes from TPM to the real numbers. So it's an element of the linear functionals on TPM, the real linear functional. Then later on, these are going to become complex linear functionals, but for now, they're real linear functionals. And the way we define this is that VP is an element of TPM. So then this is equal to the directional derivative in the direction VP of F. We're literally just using what we have over here in order to derive this. So what is the change that we made so far? This differential, what it stores is the change in every direction. It stores the change in every direction of F, right? That's what this map contains. When we give it a vector VP, what we've done is that we've told it, please give me the directional derivative in this direction. And so it spits out the directional derivative at VP of the function f. That's what we call the differential at point P of f. So that map is f, the map that we're talking about here. So right. And here we're going to have to do something with equivalence classes again. We're kind of doing something that is analogous to what we did last time with the curves that were all the same, that had all the same derivatives, right? But now think about the fact that we could have more than one germ that had the same differential at a point on the manifold. And this is a lot harder to visualize, so I'm going to try to do a good job here of kind of bringing this idea forward of what it means for two germs to have the same differential. Because this took me a good bit to figure it out. Also, shout out to Otonu for helping me figure this out. So we have a bunch of functions, right? And we're taking these functions in a neighborhood around P, and we're taking, in some sense, their linear change in that function. So we want to equivocate all of the functions whose linear changes in every direction are the same. So they have the same differential, right? So the differential stores the change in every direction, not just one direction. So we need all of the functions whose uh, behavior around P, meaning their linear behavior, um, is the same in every direction. So that means that what we really want is, well, let's draw a linear function here. Well, what can my function differ by? Well, it can really only differ by a constant function, right? Um, Otherwise, we would change its linear behavior, much in the same way that, like this is just an analogy, but y equals mx plus c. If we added anything that was proportional to x, then we would change its linear behavior. If we added anything proportional to x squared, we would turn it into a quadratic function. We definitely don't want that. So we can only add a constant amount. So we get this stack of planes, one plane for every value of c. And we're saying uh, all of these germs are the same for us. For our purposes, these are the same object, or these give us equivalent information. So these result in the same covector. So we say that DFP is an element of DGP, the equivalence class, if DVP of F is equal to DVP of G for all VP at element of TPM. For every direction, if we have this, I suppose you could prove probably that as long as it works for all vectors of unit magnitude, it would work, because then you're just scaling. But we don't need to be that fine-tooth combed. So we're just going to say if it works for every element of TPM, meaning that what we're really saying here is that what if their directional derivatives agree in every direction, and for every vector? Then we say that DFP, the covector, is the same as DGP. Right. So once we, again, what we're doing is that we have this larger space, and we're putting from this larger space, we're putting these things into buckets. We call one of the buckets, so yeah, we're going to call these with Greek letters. So one distinction I want to make right now, maybe that'll help you keep parsing everything, is that whenever I write something that's meant to be a covector, it will always have a Greek symbol. And if I draw something that's a vector, they will always have a Latin symbol, meaning an English letter. And that will differentiate us between the covectors and the vectors. Okay, so then there we have beta p, we might have gamma p. Don't confuse this with the curves. In fact, let me just call this something else. Let's call it epsilon p, I suppose. We can't use delta. Delta is something else. So, right. And these bins, just like the bins in the vector space example, these are the covectors. These are covectors. Or rather, sorry, these are not the covectors. These are the functions, and associated with each of these bins is one covector. Okay. So, right. So alpha p is equal to dfp, where where f comes from that fp. That's the germ. Fp is an element of this group gp. In fact, I have to correct myself here. This is not right. What we want to say is this. We want to just talk about the germs, not the differentials of the germs. Okay. Right. So, uh, this is a covector, and if we take the set of all of these, so for every unique, well, I don't know if this is an actual symbol, but for all unique FP, Um, well, okay. I think that it's better if we write it like this. Then this is the cotangent space, TP star M, or TP star parenthesis M if you'd prefer. Um, and because so TP star M contains elements, if alpha p is an element of TP star M, then alpha p is a function that takes something from TPM to R. The space of linear functionals on a vector space is called its dual space. So the reason why we called it TP star M is very pointed, and it's because TPM and TP star M are dual to each other in this way. There is actually an isomorphism between the two, although Otonu would probably want me to say that uh, the isomorphism is not natural, a not natural isomorphism. So it's a coordinate dependent isomorphism is the idea. Once you define some coordinates, you can show that the two spaces are isomorphic. Um, so, right. And there's a really nice relationship between the two. But in order to talk about that, we first need to talk about I'm going to skip over the way that the covectors form a vector space because it's very much the same thing as the derivative way that we did it before. You can add the covectors, right? I'm just going to write that dfp plus dgp. That's obviously defined using the fact that they're using the directional derivatives. And then once you decompose it in terms of directional derivatives, then you figure out how to add them together. Um, and scaling, similarly, you just multiply it, and then that multiplies the directional derivative map, right? We know how a map is scaled, so a function is scaled. So then that tells you exactly how to scale this. So we have addition, we have scalar multiplication. Getting a little lazy here, but uh, zero, there's obviously the zero differential. That's the constant function, right? So we're talking about linear behavior here. So that's the constant function. So if f p is equal to 0, that gives you the zero vector. And the inverse is, well, if we're adding the linear behavior to each other, right? So then one germ that's sloped in one way and the other germ that's sloped in the with the negative gradient of that, those vectors will cancel each other out. So there you go. Those are the inverses. Uh, so we got those. So this is a vector space too. But remember, here there's an interesting thing. Xi are coordinate functions that we defined last time. These are functions, right? These are functions that we can use on the manifold. So um, these are part of CP in infinity M. So what if we took the differential of these? Well, these end up being our coordinate covector basis. So this gives you that, and then that uh, is defined to be the directional derivative along this function, which then we are now defining a basis and we're trying to evaluate that. That gives us partial xi, partial xj. And then this we know, this is regular multivariable calculus. So this is delta ij. And then this is called the Kronecker delta, if people haven't heard of it, Kronecker delta. It gives you 1 if I and j are equal and 0 if I and j are not equal. And so we can think of it like if I and j were not equal, then we would get 0. So we can replace I with j. So we get VPJ. It gives us the coordinate, right? So I don't think that the indices work out here. Yeah, that's how it should go. Um, right. So the coordinate covectors, what the coordinate covectors do is they return you um the coefficient of the ith coefficient of the vector from TPM. So you can see again here how you would get the gradient using these covectors. So well, we do know that we have the coordinate basis in the vector space. So what happens if we act this on the coordinate basis of the vector space? Yeah, it's taking the coordinate basis. In fact, we call this gamma, right? So I'm just renaming gamma to x in this situation. So these two are defined with respect to the same object. This set of, did I erase it? Yeah. The coordinate functions, right? So this is defined with respect to this, and this is defined with respect to this. This is why they both appear with the same symbol in both of them. And that should give you the clue that these are dual to each other, but they give you delta ij. And this is, so these are the coordinate covector basis, useful in when you need to compute something with the covectors. Again, and then we can decompose this. I'm going to skip forward a little bit, but if we take alpha p of vp, we can decompose this into we can use the directional derivative. Uh, yeah, this will eventually give us partial. We're associating alpha p with the germ fp. So then that gives us partial fxi vpi, which then you can say that, well, what if we do some interesting index manipulation, xj delta, um, let me just follow what I've got over here. Right, so I did the other way around. So yeah, so we're replacing VPI with delta ij VPJ, which is the opposite of what we did here. And then we know that, okay, well, that's this. So that's delta xi p. Yeah, that's partial f partial xi dxi p into partial xi at p of vpj, right? So that's actually just vp, right? From before. So then this must mean that this is alpha p. This part is alpha p. I'm being a little loose here. The specifics are done in the notes and they're rigorous in the notes, but this is alpha p. So if we were to write alpha p in and we decomposed it in terms of a basis, how would we write it? We would write it like this. I'm going to use Greek letters for the covectors. So instead of E, we have epsilon here. So then epsilon is this and API is this. So this is the covector coefficient. Okay, so this is how you decompose it. And we have one last thing. I'm not going to go to the next page because we have just one thing left to talk about, and then we're done, which is that in general, I don't think we prove it over here, but right, two things. So first of all, let's see what these bases look like, these coordinate bases. So right, let's say that that's x1 and that's x2. We're going to use again the 2D metaphor here, or analogy. So um, in 2D, we would have two of them. We would have E1 uh, points in the x1 direction. Sorry, it's covariant. And E2 points in the x2 direction. So these are our basis vectors. They point along the coordinate axes. And uh, these ones are kind of the ones that we're more familiar with, but I'm drawing them so that I can tell you what the basis covectors look like. Um, in fact, let me make sure that these look like they're the same size because it'll be important. Otherwise, the diagram will be hard to draw here. Right. So then we have the basis covectors. And remember how we were talking about these like stacks of uh, constant functions? So this is the stack of constant functions. We're drawing them at unit um, interval from each other. So each of these lines is 1 unit away from the other one on the coordinate space. And these are vectors, so they're also oriented. So the way we think about the orientation is we draw an arrow next to them. So these lines are pointing in this direction. And if this makes you think of like one of those maps, like um, how like they draw the geology like that, that's actually a covector field. So we're going to get to covector fields next time, but those kind of maps, they actually should, instead of arrows, they have color gradients to show which way they point. But those are actually also examples of something that could be modeled by a covector. So this is you could say this is epsilon 1 and epsilon 2, which I'll draw in a different color just so that we don't get lost in this diagram, is the one that goes in the other direction. Okay, I think we get the point. I'm not going to draw all of them, but they span up to infinity. Like you'll draw them all over the place. So this is epsilon 2. And so what do covectors do? Well, covectors, like they're linear functions that take a vector and then they output a number, right? So what covectors do, in fact, I didn't draw this quite that well still, because it should just come up to the ending point of the first vector. What we can think of covectors as is this function that there are these lines. So let me draw an arbitrary covector. So this is a covector that has some component in the x direction and some component in the y direction. And let's say I have a vector, and let's say this is the origin point of that vector. So what the covector tells us, like how it takes in the vector in a geometric sense, like this will be different for different use cases. What you mean, what you're using the how many times does it intersect with this covector in a geometric sense? If you're thinking about it purely geometrically, how many times does it intersect? So it intersects once. We don't count the one where the vector is rooted, and then it almost gets to the next one. So this is interesting. So it won't give you a natural number. It will give you a real number, and it will tell you how much percentage of along this perpendicular, how much percentage of the way was it able to get through to in an effort to intersect with the next parallel line, and then it failed. So let's say that this is about 80%, just for the sake of argument. So then this would return you 1.8. That's how this would work. So that's the real number that you get from applying this alpha p on this vector VP. Okay, so now that we know how covectors and vectors are related to each other, there's one last thing. This was the thing that I was talking about. So if you generalize this idea here, we'll just do it here. Let me do that in a different color. We generalize this idea. This actually works for any pair of dual vector bases. So this is something that one would need to prove, but for the sake of this lecture, I'm just going to tell you about it. Um, if we take a general covector basis and we take its dual basis, so we're always going to think of epsilon I and EI as the dual bases to each other. Whenever I draw epsilon I and EI in the same place, you should take in your head that this actually means that these are the dual bases. So that means these are give you delta ij. And this is something that we'll be using next time. This is called the bi-ortho normality condition. And this works for any pair of dual bases. So if you choose a vector basis, then you construct the dual basis of it, the dual covector basis, this will work. Or if you start with a covector basis and you derive the dual basis, which is its vector, the dual vector basis to it, this will work. So, and in fact, this is how you could construct it. You could require that epsilon I, EI is equal to delta ij, and that will give you the dual basis. Okay, so that's about it. I think I want to go over a few caveats now that maybe it would have been more pertinent to go over them as we talked about them, but I missed a few things. One of them is functions versus maps. This is a very important thing. So in Chernchen and Lamb, this is a fairly old book. It's from the 1980s, I think. And so that they make a distinction between the word function and the word map. And this is something that some authors in differential geometry have continued to do. So it's something that maybe is important to keep in mind, that when some authors say, you will think that, okay, well, they haven't specified this word enough because I don't know where this map comes from and where it goes to. So like the inputs and outputs, but um, those authors are they call what they call functions are maps that go to the real numbers. So let me just draw that here. So maps. Let me go back to the place where I talked about this. I think I talked about this right under cotangent spaces. Maybe I removed it. I'm not sure. Oh, it might be in the, yeah, this might be a point in the second lecture actually, but let's talk about it. So if the codomain is R, then sorry, I've done it the other way around. This is a function from the manifold to R. And it's a map if it's from what they're calling like a space to another space. But what they mean is like some sort of structured space. So in this case, the structure is the manifold structure. So a map to them is something that goes from M to N, where M and N are both manifolds. Or it could be like it goes from T to R, where T and R are both topological spaces. So that's what they call maps. So if you see this word in the book, don't get confused. This is what they mean by that. And uh, it's not as far as I remember written in the text. It was kind of maybe like a convention at the time. Um, the other thing is that so today we defined tangent spaces on the manifold and cotangent spaces on the manifold. So we started by defining, so let me do a recap while I make this point. So this is a note I want to make, but it also goes well with the with the recap. So in summary, today we went from a smooth manifold and we defined two spaces, tangent spaces and cotangent spaces. When we did each of these, we defined something on Rn, and then we took an equivalence class. The equivalence class was supposed to put into bins all of the objects which had the same property that we were interested in. In the case of uh, tangent spaces, that was their velocity. That's the idea. That was the idea that the equivalence class was trying to get at. And with cotangent spaces, it was this idea of the linear behavior. I wish these were a little bit like more obviously dual to each other, but yes, that's the idea. So and then we use that to define the vectors themselves. So cotangent vectors are also vectors. So yeah, that's actually note number 3 is why cotangent vectors are also vectors. Um, right. But let's finish this one first. So then we define the vectors, and then we define the vector spaces as the collection of those or the set of those vectors at singular points on the manifold. So every point on the manifold has attached to it both of these spaces. Each point P and M has a vector space TPM and a covector space TP star M attached to it. So uh, so what was the note? The note was right. The note was that we could have defined cotangent spaces. So what we did was we used the definition of a tangent vector to and then we used that to remember in the directional derivative we yeah, so when we define this there's something missing, which is we went from here to there using the directional derivative and in doing so, we leverage the definition of the tangent space to define the cotangent space, right? Before we started coordinatizing them and showing that they're dual spaces to each other. But uh, in Chern and Lamb, they do it the other way around. They go with the germs of functions and stuff like that. They don't make any reference to the tangent space before they've defined the cotangent space, and then they use the cotangent space to define the tangent space. Because they're both dual, they're both on equal footing, you can do it either way. And in fact, what I was thinking is there's a third way to do it, which is you could define them separately from each other without reference to each other, and then show that they're dual to each other, which is kind of what we did here, in some sense. I don't know if that completely tracks, but because we use the directional derivative, we didn't completely do it independently. So this what I showed is kind of like a little bit of a mixed approach. But yeah, so but that method is much more hard to understand. And so therefore this is one of those places where I chose to deviate from the book and do it. This is the more common way, defining the tangent space first and then defining the cotangent space with relation to the tangent space is more common. And that's why the tangent spaces has the main name and cotangent space has the co-tangent space. So that's why the name works out that way. Um, so right. Maybe it has something to do with category theory, but I'm not sure about that. So don't quote me on that one. Um, so the third thing is the third point that I would like to make, and this is the last point, is that we call tangent vectors are what we used to call just vectors in high school. But this is a very confusing name because tangent vectors are not the only kind of vectors, and they definitely don't deserve the moniker of like vectors overall. Because when we get to mathematics, higher level mathematics, vectors are elements of vector spaces. And there are other vector spaces that are not tangent vector spaces. For example, the cotangent vector space or the space of matrices, the square matrices. Those are vector spaces too. I guess maybe rectangular ones are also, if you only count addition and scalar multiplication. But like GLNR is definitely a vector space, for example. Um, so uh, so those spaces are not tangent vectors. They're not tangent to anything. They're not, you can't think of them as arrows, like just like how we thought of covectors. Covectors are not arrows. They are parallel oriented parallel stacks of planes, right? In 2D space, they're lines. They're planes in any dimension are n minus one dimensional spaces. So in 2D space, they're lines. In 3D space, they're 2D surfaces. In 4D space, they'd be 3D surfaces. So they're stacks of those planes, hyperplanes in parallel. Um, with a certain orientation. And there's nothing to do with arrows in them. So calling tangent vectors is a very uh, bad thing to do in differential geometry. So either we'll call them tangent vectors, or in analogy with covectors, we're going to call them contravectors. I thought I came up with the word contravector, but I saw someone else use it in a book. So I think other people have also thought of the idea of calling them contravectors. So contravectors are a kind of vector, and covectors are a kind of vector, and tensors are a kind of vector as well. Um, they all are elements of different vector spaces, and tensors are elements of tensor spaces, which also count as vector spaces. So keep this in mind. Like keep in mind the distinction between uh, what you would call Euclidean or arrow vectors versus uh, elements of vector spaces. And I would say prefer this second definition when we're talking about mathematics, especially element of vector space. And this is the vector that's like more important. So I would discourage people from calling these things just vectors because it can get confusing. Okay, so that's it. That concludes this uh, lecture one. That's part two. Next time, we're going to talk about, so next time, we're going to talk about complex manifolds. Complex manifolds are in some sense simple because, uh, or their definition is simple because we've actually done most of the groundwork. A lot of the times, taking R to C will suffice. But there's one thing where we have to be careful, and we're going to get to talk about that next time about the definition of complex manifolds. But most of the next lecture will be on um, well, it will be on complex manifolds, but we won't spend too much time defining them and talking about them. Most of it will be spent on the complex structure. Remember, we um, talked about the differentiable structure, right? The CR differentiable structure. Um, differentiable is a weird word to put in that, I think, now that I've said it a few times. So, uh, but differentiable structure makes it sound like the structure itself is differentiable. The complex structure makes something complex. Um, so what does it make complex? It makes it makes a vector space complex, and we're going to talk about how a complex structure makes a real vector space into a complex vector space, and we're going to need complex vector spaces because when we do complex manifolds, they're going to be locally homeomorphic to patches of Cn and not Rn. And we're going to look at some results on complex structures, and how they act and what their behavior is. All right, so that's it for today. See you next time, and goodbye, everybody.